Hey everybody, Mr. Smith here. Great to see you. What I'm going to do today in our short slide deck is to round out our discussion of vectors by jumping on the topic of projectile motion. Now, you may remember when we started talking about vectors, we said that Galileo was considered the granddaddy of modern physics because he put math together with observation of reality in a way that was stronger than anyone had done before. And because he was the first guy to really understand inertia, that led him to the right answer on something that was fundamental. In 1637, he writes a letter to one of his friends and says, I have mastered the science of projectiles. And so what you see here is equivalent of a cannon. You see the trajectories of cannonballs that are falling if I fire with a little bit of gunpowder or if I fire with a lot more gunpowder. The central discovery that Galileo made was that the X motion, so the side-to-side motion of that cannonball, and the Y motion, the falling motion of the cannonball, were independent of each other. So X and Y, independent, they're just two things happening at the same time. So we're going to really put that at the center of our discussion today. Isaac Newton, in publishing what becomes really the founding documents of physics, this thing called the Principia Mathematica, uses and extends Galileo's idea about vectors and globalizes it to actually include an orbit. So what you see here is the same diagram. You see a cannon firing off of a really tall mountain, and you see the projectile landing farther and farther, except when you do it on a curved Earth, eventually, if you shoot far enough, fast enough, you can actually put a thing in orbit. So our discussion of circular motion, the next unit, is actually going to flow out of this one. So anyway, let's get right to a couple of problems. Take good notes on these, submit them, and you're good to go, and you'll be able to do all the problems that you need to do in our unit today. So to begin with, I've got one of those physics images that's really worth 1,000 words. We're going to do it in a lot less. This is a strobe image. So a strobe camera that's flashing really rapidly, let's say every 5/100ths of a second or something, is used to expose a falling ball. In fact, two falling balls. The purple one is just released and let to fall to the ground. The orange one, at the moment that they're launched, is given a little bit of a shove to the side by this ball launcher up top, and then after that there's no more sideways forces, and so that ball falls to the ground. I wanted to point out two things about this. The sideways motion first. What I did was I took the original image and I laid over the top of it a bunch of white lines, and I used the PowerPoint spacing tool to make sure that they were all evenly spaced. And I'd like you to pause the slide deck if you want to. But what I see here is that when I line up the first white line with the first ball, all the other ones fall perfectly into place. And what that says to me is that when there is no air resistance, that means no sideways forces back or forward on these balls, the X velocity is just very simple. It's just constant. And what that lets us do is when we're thinking about projectile motion, understand that the X position of a thing uses the first equation we ever studied. X naught, your original position, plus Vx, your constant horizontal velocity, times t, done. So X motion is constant. Next thing, what it is, if I take off the white lines and let you see the original underlying image, they gave us these horizontal white lines at even physical spaces. And what I see is that I get 1, 2, 3, 4 dots, for example, and then I get 1, 2 dots, 1 dot, 1.5 dots, 1.5 dots, 1 dot. And what I'm seeing in this is accelerated motion, right? So clearly in the Y direction, there's speeding up going on. But what's cooler than that is notice how the two balls track. And again, don't take my word for it. Pause the slide deck and look at it yourself. But what I see is the purple and the orange tracking perfectly side by side. So as they fall, the fact that the orange ball is moving to the side has nothing to do with how it's falling. So that's huge. Horizontal and vertical are independent. And what I can do now is I've adapted two equations. This is just accelerated motion. So in the Y direction, the Y velocity of the ball, and I'm pointing at this one down here, is its original Y velocity plus acceleration times time. The y position of that ball is going to be its original y position plus its original y velocity times time minus 1/2 at squared. And what I've done, you can see, is I'm using g equals 10, and I'm assuming that downward's the minus direction, so that's why I've adjusted these equations the way I have. But you're familiar with these. So what I'm going to do is jump on two examples, and if you do a good job with these things, you should be all set to go and handle any of the problems that are coming your way. So to begin with, I want you to notice that this is the first type of question. This is a person that's doing exactly what the balls did. Manuel is going to leap out this way horizontally from a high thing. So you're really looking at half of a parabola here. We're not launching Manuel up from the base of the ocean and having him fly across the air and land in the water. So what I'm going to do is just read it, pause if you like. The dy is going to be 22 meters here. I'm going to use that to figure out how long he's in the air for, and then we'll work from there. So my y equation is y equals y0 plus v0 yt minus 1/2 of gt squared. And I know for a fact that if Manuel just jumps horizontally, there's no y velocity to his original motion, that this component just doesn't exist. So this problem gets pretty easy. And what I want to do is just learn how long does it take him to hit the water. So when is his y position equal to 0? Okay, so his original y position was 22 meters. And 1/2 gt squared I can handle. That's minus 1/2 of 10 meters per second squared times t squared. And I'm just going to jump down here and chop off the labels, I think. So t is going to be the square root of 2 times 22 divided by 10, and when I take the square root of that whole shebang, I get that he is in the air for 2.1 seconds. Okay, so pretty long hang time. And now what we can do is figure out how long does it take him to get this far. So I think that's about right. They tell us this is 5 meters. So he's going to have to, let's go and pick a little bit different pen color, come down here. I think that the Vx he's going to need to have is going to be the distance he needs to cover divided by time, that this Vx is going to be constant, and it's going to be equal to 5 meters over 2.1 seconds, and I think I can just about squeeze it in down here. So I get around 2.4 meters per second. Okay, so that's the first type of example where you have something going from a high place to a low place. Okay, so let's take a look at the next one. In this example, we're going to study somebody that launches, literally launches. Now, this is a long time ago. This is 2008. It's one of the good images on the internet of a long-distance dirt bike jump. And it's also one of the ones where the guy doing it didn't die. These are so hazardous. I don't know if they've stopped this, but there was a lot of loss of life in this long-distance sport because landing these jumps is really hard. If you notice in real life what they did is, this is Ryan Capes, they put the camera somewhere over here near the landing zone, down around this way, and you're looking at a skewed perspective. This really is an awesome parabola, except because they kept him alive here, they landed him significantly higher than he launched from. That's because as he travels upward, he's going to lose y velocity. So his x velocity is going to be constant for each one of these motions, assuming there's no air resistance. And what you can see by the trajectory is that the y distance that he travels gets less and less until at the top there is no y. But what happens is as he falls, his x is still constant, but his y gets bigger and bigger and bigger, which means it adds together with the x. So the velocity that he can end up with could be 100 miles an hour. And you can take off going 100 miles an hour, but landing it, almost impossible. So let's go and jump on the actual science of this one. Here's his actual takeoff speed. It was around 100 miles an hour, 45 meters per second. They give us the dirt bike ramp, which is about 40 degrees from the horizontal. Regardless of what they ask you for in these questions, your strategy is always going to involve doing this first step. You're going to draw a vector picture, and let's see if that's around 40 degrees, okay? And this is going to be my 45 meters per second. So as I work through these things, you can really feel free to shut this off and do your own work. And I'm going to do the same thing at some points, and I'm going to not make you listen to me figure these out, but I'm going to go and do a Vx equals 45 cosine of 40, and that equals 34.5. You should show your work. Vy is going to be 45 sine of 40. You should show your work, but I'm just going to race through it. 28.9 meters per second. And so part A is done. Now, what I do is pretty standard with this next unit too. There's a lot of complexity to somebody rising and falling, but one of the things that I can hang my hat on time after time is that when a leaper or a dirt bike rider, whoever it is, gets to the top of their motion, their Vy at that point is going to be 0. So at the peak of the motion, the Vy goes away. And what that lets me do is to study that V at any moment is going to be equal to V0y minus g times t. And so let's leap on it. So Vy at the moment I'm talking about is 0. So V0y was 28.9. And let's go minus 10 meters per second squared times t. And so what I do is I get this pretty easy formula. T equals 2.89 seconds. It's really important to bear in mind what that is. I'm going to give it a special code name. I'm going to call it T1 half, because that's the time it takes him to get to the top part of his motion. So they're almost always going to want to know what was the total time. Well, if we have real symmetry, and we usually do, T total is going to be twice this much. So let's go to the next one. We'll wrap it up. So assume that the rider lands on the ground. Question C, how far does he go? This is just going to be dx. Constant velocity equals Vx times t. So this is going to be 34.5 meters per second. And remember that my half time was around 2.9 seconds. I'm going to give him 5.8 seconds here for his total time. So 34.5 meters per second, 5.8 meters per second. That is just around 200 meters of jumping. And that would be if he leapt from the ground, landed on the ground. And in real life, that's probably not survivable. So nobody lands going 100 miles an hour and rides it out, unless they're on a really big downhill. So let's go ahead and check out D. A little more realistic version and a more complicated version is to say, what was the total length of his jump if he landed on a berm? That's what you saw him landing on, that big ramp, 15 meters high. So that's 45 feet in the air. Now to get this one, what I'm going to need to do is find the time. So I'm going to go and say y equals y0 plus v0y times t, and minus, let's go simplify it now, minus 5t squared, okay? Let's think about it now. Y is his moment at time t. So y is his height at time t. That's going to be 15 meters. His original height was 0. His v0y, he did have that. That was 28.9 meters per second, remember. Now, what we're trying to solve for is the time t when that happens. So what we end up with is a quadratic. So minus 5t squared. So if I collect this whole thing together, what I end up with is 5t squared minus 29, let's call it 29 times t, plus 15 equals 0. And when I go and figure out that time, I get that t is around 5.2 seconds. There's actually two solutions for it. One of them is very early on in the game, and the one that we want is 5.2 seconds. And if they want to get the total length of his bike jump, all we need to do is just use the fact that, again, dx equals vx times t. He's always going to be moving 34.5 meters per second. And if he does it for 5.2 seconds, we get a fairly shorter, let's see, I got it figured out over here, something like what? Yeah, 180, 179 meters. Okay, so that'd be his length when he had gone, when he was 15 meters high. All right, now in real life, final thing, his actual jump was 119 meters. That's over 300 feet. That's 390 something feet, like 391 feet. It's bananas. And yet it's significantly shorter than this. So in real life, for motorcycles going 100 miles an hour, air resistance really does play a huge role. In our lab, not so much, because the speeds we use are slow and the objects we use are going to be small. Anyway, that's enough for today. What you've got is all the stuff you're going to need to go ahead and do a few short problems to just stay in practice until I see you next time. So have a great day, take care of yourselves, and keep on doing physics. Bye-bye now.